So we completed our example with m is equal to 2 for the whole forecast last class, and later on we're going to look at linear regression. So I want to take a look at how, and linear regression is the other method used to identify the trend pattern in time series. So looking at the Holt's method versus the linear regression is much like the cumulative mean, which puts the same weight or equal weight on all historical data. For the Holt's method, just like the simple exponential smoothing, that weight changes depending upon, in this case, how the trend develops over time. And so you're seeing the weight evolve according to the nature of the time series. And the way we can adjust how much that weight changes is by changing the parameters. So we saw that increasing alpha and beta is going to increase the responsiveness, but also the nervousness of the Holt's model. So that is something that is similar to the simple exponential smoothing. So we need to adjust those values of alpha and beta to match the right type of, to calibrate it to the type of time series that we're looking at. Finally, with the Holt's method, we look at a method that only needs maybe 3 or 4 periods of demand versus the linear regression that requires maybe at least 10 or 12 periods worth of demand before you get an accurate estimate of what the demand, what the parameters are. So, and you might be wondering, how do we know what the pattern is? Usually, you are forecasting an item that is new, but that is related to some previous item. So, for example, it might be a new packaging of detergent. It might be a new size of detergent. It might be a new labeling. It might be a different case. You might have 2 per case, or you might have 4 per case. So, the actual item itself might not have changed intrinsically, or if there is some intrinsic changes. For example, if you're selling Dr. Scholl's insoles, you might have some intrinsic changes in that. But essentially, the use of the item is the same. You're still using it as an insole, right? So the function of that item does not change. So it has some relationship, and so you identify that these are the typical patterns, and so we're going to use these methods, and so you have less data to use in those cases. So the next method we're going to look at is the Winters model for seasonal data. And to forecast the demand at period t plus m, we need to use the level at period t, multiply by the seasonal index at period t plus m minus s. So this, as before, is the level at time t. And this is the seasonal index. So a little bit of background first before we move into the calculation of the level and the seasonal index components. So from this, if you're thinking of forecast as the actual demand, but at some point in the future, theoretically we can look at it and say the demand at time t is equal to level at time t multiplied by the seasonal index at time t, right? So in other words, the demand at any time is a product of the level and the seasonal index. Okay? So let's see how that works. You've taken this down? Oh, wrong one. So I have a time series that goes something like this. Clearly there's seasonal pattern over here, right? The level or the average of this time series, let's say, is 100. Yeah? And the peaks and the valleys, so the peaks will be 120 and the valleys will be at 80. So that's the demand at the peaks and the valleys. So because of that formula that demand is equal to the product of level and seasonal index, I can see that my seasonal index at all of these peaks is going to be equal to 1.2. And similarly, the seasonal index at all of these values is going to be equal to what? Can anybody tell me? 0.8, right? So clearly we know that the demand at these peaks is going to be equal to the level, which is 100, multiplied by 1.2, which is equal to 120. And ditto down here. So in other words, the seasonal index is just moving the level up and down by a percentage of the increasing or decreasing of demand compared to the average of demand, right? That's what it's doing. And we see later on that the seasonal index is essentially always going to be, in our case, a value close to 1. But we can also have other types of models that use different types of seasonal components. All right. So, if everybody's okay with this, I'll move on to our example or the calculation of our components. So that's the demand defined by the level and the seasonal index. Now, with simple arithmetic, just rearranging these terms, I can also calculate what the level term is, which is the demand divided by the seasonal index. And I can calculate what the seasonal index is by taking the level demand divided by the level. And we're going to use both these methods in both deriving our formulas here as well as in initialization. Okay? So let's look at our formulas first. Has everybody taken down those three functions in the middle? I won't have any space for myself. I've squeezed myself out. Taken down those three functions? Anybody still writing them down? Okay. So I'm just going to erase these to give myself a little bit of space, or maybe just the bottom one. And probably rewrite it maybe. So there you go.
Seasonality, that's still alpha there.
For seasonality, this is I use this as the lowercase gamma.
Okay.
So I can't quite do this, or is it supposed to be like that? So I think that's what gamma is supposed to look like, but that's my approximation of what gamma should be, lowercase.
So for level, that is an alpha, but for seasonality, that's a gamma.
That's a gamma, yeah. Okay. We're running out of Greek symbols over here. Well, we're not. We'll start running out of it when we do other stuff. All right? So, let's do a quick example. But before we do an example, I want to point out a couple of things over here. So, obviously, I need to understand how to initialize my level and my seasonal index. And I said it's going to be very similar to those three functions I gave you, which is what the theoretical level and seasonal index should be. Okay? The second thing is, I've given you my alpha and gamma. And again, it's not unlike calculating what should be my my alpha when I'm doing simple exponential smoothing. As I choose different values of alpha and beta, and then I see which one minimizes my my mean square error. Okay, which one gives me the lowest mean square error. So clearly that we can deal with. We've understood what m is equal to. I'm giving you m is equal to 1 because that's our planning horizon. But what about this s is equal to 4? Okay, so here we have s is equal to 4. Now that's something you're not going to get in real life. You're not going to get on the homework even. So how do I know what my s is equal to 4? How do I know what? First, what is s? S is the number of seasons that I have. Okay, so I should have pointed that out here. So you can go back, and this should be number of seasons. Okay? And that is a small lowercase s. Okay? So how do I know what this lowercase s is actually? So the way I do that is I find some striking characteristic of the time series. It's going to be either a peak or a valley, right? So in this case, the valleys seem pretty consistent, so I start at the first valley I know. And remember that there is an imaginary hash marks over here, which is telling me which period I'm at, right? In Excel, when you plot it, you can use your markers, right? You know the markers, if you plot a line, you can use the markers of the line. So here, unfortunately, I don't have the markers, but I know the data well, so I can start counting at each period. And then before I come to the period where I started, or the season that I started, I stop counting. And then I start counting again. So that's 1, 2, 3, 4. And then again, I start at the valley. It's 1, 2, 3, and 4. Right? And I keep doing that. And so clearly now I can see that I have 4 seasons. So my lowercase s is equal to 4. Okay? And you'll do the same thing in your homework. You'll find some clear characteristic. You start counting from there. And then before you get to that part again, either peak or valley, you stop and then start counting from that point again. Now another thing that I want to point out in our formula, so I'm going to erase this now. So if I'm sitting here at this period, I'm sitting here at this period. Okay? Well, let me pick something a little bit more clearer. Say I'm sitting here at this period. And I'm trying to forecast my demand for the next period. Now, which seasonal index will I use? I'm not going to use the seasonal index for here, right? Because from the example that I showed you, you cannot use, for example, the extreme case, the peak seasonal index for the valley, right? So in this case, I have to look back to the last time when there was a peak, which is 4 periods ago, 4 seasons ago. So counting backwards, 4, 3, 2, 1, 4 periods ago, that's when I had a peak. So that's why the subscripts for S is always T minus S, or T minus the number of seasons. Right? So that's another easy conceptual way to understand how to get my seasonal index. Okay, so now let's do a couple of examples here. Any questions about this so far? Okay. Let's start by trying to calculate the level for period 16. So what is my formula? It's alpha. So what period's demand should I use? And what period's seasonal index should I use? Oh, there's one more thing. Let me point this out before I go forget. So remember I told you last class about the simple exponential smoothing. You have alpha times the real information plus 1 minus alpha times the estimated information. For level, this is the real information. And this is the estimated information because it's the last estimated level that we know. Similarly for the winters, similarly for the seasonal index, this is the real information that we know for the seasonal index. This is the last estimated information that we know for the seasonal index. So it's the same principle. Okay, so going back to our calculation for level 16, which period's demand and seasonal index should we use? Plus 1 minus alpha. And in this case, we have which period's, which period's level should we use? So what is that? What number is that?
67.
Sorry?
The D would be 67.
But which period is that?
16.
16, exactly.
Excuse me.
So D should be 16. What about S and L?
12 for F.
So 12 for S. I'm only writing this down. I'm not confirming it. And what should it be for L? 15. Okay. Everybody agree with that? I'm crowdsourcing this now. See? We can crowdsource accuracy, right? Estimations. Is that correct? But more relevant, I mean, the more pertinent question is, do you actually see how we came up with these? And these are correct. Do you see how we came up with these? So we know that T is equal to 16. So we go back to the formula, D is used for time T. So that demand is times 16. S is for T minus S. So 16 minus, what is S? 4, right? So that's 12. So that's how we got S12. And the L is T minus 1. 16 minus 1, which gives us 15. Is everybody clear about that? Good. So we have alpha, which is 0.2, multiplied by 67, divided by 0.66, plus 1 minus alpha, which I'll just take as 0.8, multiplied by 103. So our level 16 is equal to 102.7. So in your notes it's 103. It's incorrectly put down over here because I had the wrong rounding function, so it's 102 over here. But it should be 102.7. Okay? So, if everybody's got this, I'm going to... Yes, Andrew.
I have a question. On the homeless, what place did you want us to write?
It's chemicals, right? And what's the units? Tons, right? So, round to 3 decimal places, I think, would be... For working, you don't round. You don't go around for working. But for displaying, I would say just display till 1 decimal place. Because that'll work in 100 weights, which would be sufficient. So the principle for rounding is you see what you're working with and what your weights are, what your units are. Yeah. So if you're clearly working in grams, you can round up to integer values. Again, depends upon the context. If I'm using gold leaf, then I want to round down to maybe 4 or 5 decimal places, because that can have a significant impact per ounce or gram. Okay, so if everybody's taken this down, I'm going to erase it. And let's look at the Cecil index for period 16. So we have gamma times the demand at which period, the level at which period, plus 1 minus gamma, and we have the Cecil index at which period. So somebody who is not confident with the subscripts, let me hear from you. It's a good way of getting some practice if you want to. Anybody?
D is 16.
D is 16, L is 16, and what is S? 12. Yeah, pretty straightforward once you get it. Okay? So our gamma is 0.3, 67 divided by 102.7 plus 0.7 multiplied by 0.66. So S16 is 0.659 or 0.66. So if you finish this, look at the next example. All I'm doing is asking you to calculate the forecast for period 19, or period 18, sorry, with, in this case, our m is equal to 2. Okay? So try to do that by yourself. I'm going to start by doing the forecast over here for period 17. So what is the level for period 17, and what is the Cecil index for period 17? So once, if you figure this out, then you can start working on the next problem with m is equal to 2 for period 18. Okay, so the next one, what is the level and the Cecil index? But let's talk about this. If I want to calculate the forecast for period 17 with m is equal to 1 and 4 seasons, what period's level should I use and what period Cecil index should I use? Level 13. Again, I'm not telling you if this is right or wrong, I just want to know. And Cecil index? Is that correct? Some of you shaking your head, some of you nodding. Sorry? L should be 15, you're saying? Now this is, remember, I've been jumping back and forth, so in this example, m is equal to 1, right? So you're saying L should be 15? Okay, so now we're just pulling numbers. 13, 15, 16, okay. Anthony, you had a hand up.
Oh, he's already said
16. So what is it? 16 and 13. Okay, so let's go back to our basics. What do we know is T plus M? We know that we want to forecast period 17, right? Therefore, T plus M is equal to 17. We know that this M is equal to 1. So what is T equal to? 16. We know that we need the level component for time t, so we need the level component for period 16. We need the seasonal index for period t plus m minus s. T plus m is equal to 17, right? And s is equal to 4. So what is t plus m minus s equal to? Simple, right? 13. Is that clear? So this is correct. So forecast for period 17 is equal to level at period 16 and seasonal index at period 13. To belabor the obvious, it's 102.7. Okay? So once you figure out the subscripts, it becomes pretty straightforward. Yeah? So do the second example where I showed you m is equal to 2 for forecasting demand at period 18.
Explain that part.
Which part?
Plus and how you got that.
So I go back here, and what is my formula? Ft plus m is equal to Lp times St plus m minus s, right? So if I want to forecast demand for period 17, I know that 17 is equal to T plus m, right? I need the level at time t. So my m is equal to 1, therefore t is equal to what? 16, right? So I need level at period 16. I need to know my t plus m minus s, right? So I know t plus m is equal to 17. I know s is equal to what? 4. I have 4 seasons here. Remember I counted the 4 seasons over there? And it's also given to me here. So t plus m, this whole thing, is equal to 17. S and S is equal to 4. So this, yep. Question? So what do we have as our forecast for period 18? How do we calculate? What period level should we use and what period seasonal index?
Use 17 for the level and 14 for the seasonality.
Okay?
And it comes out to, well, the level is 104 times the seasonality is 1.06, and it comes out to 110.24. Oh,
So remember m is equal to 2, right?
yeah.
So which one do we use? 16, right? Yeah. And the thing that you'll notice is that our seasonal index still stays the same, regardless of our m, because we are taking t plus m and we are just looking back 4 periods, that's 4 seasons. Okay? Because of the pattern of the seasons, we always have to look back to the last time we had that season in the period that we're forecasting for. Yeah? So, L16 S14. So this becomes about 109, right?
What's the M mean?
M is the forecasting horizon, how far forward we want to forecast. Remember I talked about it last time, the order cycle time.
Okay. So
That-
2 order cycles, right?
Sorry?
2 order cycles are
No, no. In this case, it's 2 periods make 1 order cycle. Or 1 planning cycle, however way you want to term it.
How did you get 106? Go ahead.
1.06.
1.06. Should
That's-
be 1.07. 0.7.
Sorry?
Oh, I'm sorry. I copied the wrong number.
I was looking for 1.07 over there. I didn't see one. So is this clear? The Winters model? Okie doke. So let's look at the initialization calculation. It's pretty straightforward. So first let's look at it here. So our definition of level is the average of demand, right? Now for the Winters model, we cannot calculate the level or the seasonal index for the first lowercase s periods. In other words, the number of seasons that we have. So we have 4 seasons. In this case, we can't calculate the level and the seasonal index for the first 4 periods. So we have to initialize the first 4 periods. The average of demand or the level of demand in the first 4 periods is just simply the average of the demand itself filled in as the level, and all of the first 4 periods are always going to be equal. So we just take the average and fill out that average as the level. So the level is always going to be equal across the initial periods. And you'll observe that as you go down the level component, it should be approximately pretty close, right? That is one way in which you can judge how good your components are. If your level changes a lot, that means you maybe have to change your components, right? Because that means you're capturing the noise and not capturing the pattern of the demand. So you can even plot your different components to see how well they are performing. Okay, so that's pretty straightforward. The seasonal index is also straightforward. It is just the demand divided by the level. And if you go back to the first 3 functions I gave you on the formula page, you will see that there too, seasonal index is equal to demand divided by level. And that's how we know how to initialize the seasonal index. And so you can just take down these things, these functions or formulas that tell you the same thing, but in a arithmetic form. Once you know the Holtz and the Winters, then the next model, the Holtz-Winters model, where we forecast demand that has both seasonality as well as trend, is just an extension of these two methods. And it's really just like we learned with the moving average is the most general kind of moving average, and it subsumes naive as well as the cumulative mean. The Holtz-Winters is the most general form of the exponential smoothing, from where you can derive all these other models. So let's take a look at that. So we have if you go back to the beginning of forecasting, the first function I gave you, you recall that it was demand is equal to the level, or theoretical demand is the theoretical level plus the theoretical trend multiplied by the theoretical seasonal index. And now that you understand how these components work, you can see how this all works together. And the formulas that we're using are the same as before. So clearly we have to start with some initial values, because as you can see we still have t minus s, so we cannot forecast the first lowercase s period, which is the number of seasons, and I'll talk about that in a second. Let's do an example first. So I want to forecast my demand for period 17. So let's see how we come up with that value. So the question is, which period's level should I use? I know my m is equal to 1 and s is equal to 4. So since m is equal to 1, I'm just going to ignore it. Which period's trend should I use? And which period's seasonal index should I use? Anybody?
Level and trend should be period 16, and the seasonality should be period 13.
Is that right? Yeah? Saying nods of agreement and nods of agreement? Yeah. So we have the level for period 16, which is 151, plus the trend, which is 4.4, multiplied by the seasonal index for 13, which is 1.05. So the forecast for period 17 is 163.2. Pretty straightforward once you know how to work out the subscripts. The subscripts are just indexes to identify which period's level, demand, trend, seasonal index I need to use. And if you understand the conceptual reasons why you use different level and different demand, different seasonal of different periods, then it's a lot easier to put these two together. And then you don't even have to memorize the formulas. You can just write them out, straight out from concept. Okay. Everybody's got this? So as I saw, the value of S can be something around 1. If you're getting values of S close to 1, that is 1.02, 0.98, 0.99, 1, then you're likely not going to have a seasonal pattern to your data. Okay? So that's an important way of, what is our objective of forecasting? Identifying the pattern, right? So this is one way of identifying that we don't have the pattern in the data. Now, we learned that the demand is, or the seasonal index is multiplied by the sum of the level and the trend, right? Now, we can also have it such that the demand, the seasonal index is just an additive number. So we could have the forecast at some t plus m is equal to the level plus the trend plus the seasonal index. So it could also be some additive value. Now, because it's an additive value, clearly, if it's a peak, it would have a positive value. If it's a valley, it would have a negative value, right? Because we are reducing the average level of demand by that amount. Okay, so let's look at initialization. So for the level and seasonal index, the initialization is exactly the same as the winters. There's no difference. For the trend, you take down this formula, and then I'll show you an easy way of calculating that. It's just the same as we did for the Holtz method for initializing trend, using the moving average. All right. So, well, I just should have pointed this out earlier. I just realized there is one error here. This should be, the subscript should be 2s. So it should be 2s. Okay. So this trend calculation is exactly the same as the initialization for the trend with the Holtz model, with one important difference, where now instead of a capital N moving average, we use a lowercase s moving average. So let me explain. So here we have trend, or let's call it initial trend, is equal to the average now here we have the d lowercase s plus 1 to d at 2s minus the average at the first demand up to the lowercase s demand, and we divide the whole thing by lowercase s. So it's the same formula as we did the last time, except instead of the capital N, we're using the lowercase s. And these two formulas work out to be exactly this one here. So in Excel, you can just use this, and you can actually derive this formula. You can derive this formula from this formula right here directly. And very quickly, has everybody finished writing this down? Very quickly, what I'm really doing is, I'm just taking the first S periods, and I'm taking the second S periods, and I'm finding the average, and that rise that I'm getting, that is my initial trend. Okay? Now with the Holtz method, I needed to pick an N, a capital N, for the moving average. Here I don't have to. I just take the S is equal to the N, which is equal to 4. Right? That's all I'm doing. Any questions about the Holtz-Winters model? Initialization, conceptual formulas, anything? Okay, so you're all experts at forecasting now. We move on to regression techniques, which is the last of our topics of before we move on to the next one, part 2. So again, regression techniques, we all gone over this. We want to measure some variables that can predict demand. We talked about ice cream demand, and we said we can measure what people's attitudes are towards different assortments of flavor. We could measure how many competitors there were. We could measure temperature, precipitation, how many students were there on campus. And what we're interested in understanding what is the nature of the relationship between those variables and our demand item that we want to predict. So we can have two types of regression. The simple regression, where we are going to say that time explains demand. Time is easy enough to measure. We can measure it on the calendar, we can measure it in a clock, etc. we can have either a linear model where as time increases, demand increases in linear fashion. We could have a non-linear model where demand increases, there's a quadratic increase in demand, a polynomial increase, or we could have exponential increase. We can have all different cubic. So there's different forms. Now, with multiple regression, it's the same idea. We want to understand what is the nature of the relationship, increase, decrease, by how much. But we'll have multiple variables explaining how that demand is increasing, decreasing. We look at that after we look at simple demand. So first thing is demand. What is our objective? Identifying the pattern. We identify the pattern by understanding what is the increase and decrease in demand using this coefficient A, which is the analogy is the slope of the line. You remember the slope of the line from middle school algebra? So that's really the slope of the line. What's the tendency of your line to increase or decrease? So that's really telling us the nature of the relationship. Okay, A is telling us the nature of the relationship. B is just, what is B from the slope of the line? It is the intersection of the line with the y-axis, right? It's the intercept, or the constant, right? Or the starting point of the line on the y-axis. It might not be the starting point of the line. In our case, it is, because we're usually not going to be interested in negative demand, right? Sorry, not negative demand, negative time. There's no such thing as negative time, right? So it's an easy way to remember it, although theoretically it's not a good way of remembering it. Okay, Brian.
Are these where your forecast doesn't start until like period 4? Wouldn't that just be 0? You know what I'm saying?
No.
Because like how we can't start a forecast until we've reached the season, which is 4.
Okay, so what I should have pointed out is we are using this only to forecast demand that has trend in it, not seasonal patterns. So the simple linear regression cannot be used for forecasting seasonal pattern, only for forecasting trend. Sorry, I should have pointed that out. Okay, so this then gives us our forecast at time t. Okay? And anything else, any other error that we get in the forecast is purely due to noise. So, the way we do it is ordinary least squares fitting. The line that you see in red is a conceptual line of fit. The way we fit that line is we try to minimize the distance of each of those points from, or the square of the distance of each of those points from that line. Okay, so we're trying to minimize. So it's an optimization in a way. So we're minimizing how far those points are from that line, and we find that line that minimizes the square of those distances the most. That is the best line of fit. And that, the equation of that line is AT plus B. So clearly, we know what T is going to be. T is our time period. We need to find out what A and B is. So A and B have to be found out from what data we have. Usually the time period in numerical order and the demand. So A is found out by taking the product of the time and the demand and summing up that product from the first period to the nth period minus n times the average of demand. The way I denote average is I take the letter D and I put a bar over it, and the average of time periods T, which again is denoted with a bar over the letter T, over the sum of all the periods T squared minus n times the average of T squared. And B is equal to the average of demand minus A times the average of T. So when you plot a time series as a scatter plot in Excel, and you ask to fit a line to that plot, Excel will give you a number of options. You can fit a polynomial line, you can fit a straight line, you can fit a cubic line, you can fit a quadratic line, an exponential line. If you fit a straight line, then this is exactly what Excel is doing. It's calculating this line and it's fitting it. It's the best line of fit. Okay? And when we look next at classic decomposition, that's one of the ways in which we can calculate the trend of classic decomposition. So now that I have my parameters, a forecast at time t can be easily calculated by the product of A times t added to that my intercept b. So, in a simple example, I will start off with my data where I've serially numbered my time periods and I've got my demand for each of those time periods. Okay? That's where I start. So, it's easy to calculate what is the average of the time periods, which is 8, the average of the demand, which is 160, and then I take the product of the T and D, and that gives me my third column, which is T times D, and then I take the sum of that, and that gives me another value that I need to calculate. And then I just take the T squared. Let's use another color. The T squared to give me my third column. I take the sum of that, and that gives me another parameter that I need to calculate my A and B coefficient. So to calculate A, I need the sum of the product of T times D minus N, which is 15, times the average of D, which is 160, the average of T, which is 8, over the sum of T squared, which is 12,420, minus N times the average of T squared. And this works out to be minus 4.5. So for B, I have the average of D minus A times the average of T. So my average of D is 160 minus A is 4.5 and the average of T is 8. So B works out to be 196. So now we can appreciate Excel because Excel does this for us in a matter of a second or sooner. However, if the lights go out, you can still calculate it. Because now, if your laptop battery runs out, you know how to do it by hand. And I actually had one of my students in the Air Force working in Fallujah have to do this by hand. So that was pretty cool. Anyway, so what happens if you have to forecast demand at period 17? How do we do that? Can we do that? Let's pick something easy. What if I want to forecast my demand at period 12? How do I forecast demand at period 12? Sorry?
Plug in 12.
Where? Plug in 12 where?
4 times 12 equals A times 12 plus 2.
Exactly. And I know what A is, I know what B is, I just have to use that. So what about 17? Same thing, right? Now what if I said, I want to calculate the demand for period 35. I can calculate it, right? But would it be right? Probably not, right? It's too far out. So you have to be careful about how far forward you want to forecast. 2 periods, maybe 3 periods, probably 4 periods. Depends upon how accurate your parameters are and how accurate your forecast is so far. Gives you that confidence, and we'll talk about that next in the next class. The confidence we have in our forecast, right, to predict the future demand. Any questions about simple linear regression? Okay. Multiple linear regression, same idea. Now, instead of having a single A, we have multiple A's. And in this case, our A of 4.5 told us that demand is decreasing at the rate of 4.5 units each period. Okay, so we know what the nature of the relationship is. It's a decreasing relationship and it's by 4.5 units. So here, for each A, for each variable, we will know for dollars spent on advertising, how much is demand going to increase or decrease by. For inflation, how much is demand going to increase and decrease by. For stock market performance of a company, how much is it going to change by. And for income levels, how much is it going to change by. Weather. You can put in anything over there. As long as you can measure it, and as long as you can measure it for the time periods that you have the demand. Now here, instead of B, I'm using another form of notation for the coefficient. So this is just another way of saying B, which is A sub 0, which is the intercept of this equation. And you'll see both when you look at textbooks or when you look at papers or when you look at reports. It's just a preference thing. And with software, you don't have, I mean, the calculation, the manual calculation is very similar. You can actually derive it from the simple linear regression. It's very similar. But if you use software, all you have to have is you have to have each variable, the measures for each variable in different column. You run multiple regression, and voila, you have the nature of the relationship of each one of those variables on your demand. Yeah? So it's really, really simple. If you want to come back, then I'll teach you how to do it in the graduate program. Okay. Or somebody else will. Any questions about regression? Again, you can only use it for forecasting demand that has trend. You cannot use it when there's seasonality. Now I'm going to show you how to incorporate the linear regression in calculating demand that has seasonality, but it's not the same thing. You cannot do it solely for forecasting. So that brings us to our last topic in forecasting. How do you feel? Everybody's gung-ho about? Yeah, nobody's.
I just have a question.
Yeah.
For this, we're taking the average of everything. So if we were going to forecast up until 12, you just take the sum of everything here and do the same thing?
Yes. Okay. If you only have 12 periods.
Okay.
Okay. Now, for each forecast, so for example, I heard you say to forecast for period 12, you only have to do all that calculations for. No. If you have a data set, if you have demand, then I just calculate the parameters A and B, and then I can use that forevermore.
Okay. So you just have to drag it.
Yeah, I just have to do it once, and then I can forecast any period that I want.
Okay.
Okay? It's not for period 12, I have to come up with the sum averages all over again, and then calculate A and B again, and then calculate the forecast for period 12. And same thing for period 17. No. I need to calculate the parameters A and B using my demand, and then from there I can calculate any forecast I want.
Okay.
just using A and B.
Okay.
Does that answer your question?
Yes, it does.
Okay. So here we're going to talk about classic decomposition and confidence intervals, what's our confidence we have, and then I'll talk about some data adjustments and transformations. We'll get to that next class. First, I want to start by talking about classic decomposition, and I wanted to get to spectral. I wanted to talk about Fourier series at least, but we probably won't get to that, not now, because I'm trying to change things around. So we'll talk about classic decomposition, and just like with the Holtz-Winters, you could either have the product of all the components of the time series, or you could take an additive approach and look at it. But we are going to stick with the product of the different components of the time series. Now, since we are looking at operational forecast, we're going to ignore C by setting it equal to 1. And since we don't want to forecast, or we don't want to fit noise, we are going to take the random component and set it equal to 1, which leaves us with the classic decomposition forecast, which is the product of the trend and the seasonal component. So, now that brings us to the question of how do we calculate our trend and how do we calculate our seasonal index, right? Or seasonal component. So we could do this, we could fit a line by eye and we could see what is the rise per period. So for one period, what is the rise? And that is our trend component. We could also do simple linear regression, which we're going to end up doing. Or we could do a moving average. We could look at the moving average, see what is the average, and that rise is our trend component. But it's easier to calculate what our simple linear regression parameters are, and that's the one that we're going to use. You don't have to rewrite this formula down. I just have space for it here to remind us what it is. So if you want, you can write it, or you don't want, you don't have to write it. So now we have the A and B component, but instead of the A and B component being used to calculate what our forecast is, it's being used to calculate what our trend component at time t is. Okay? So that's a key difference. So we are now calculating what our trend component at time t is. Oops. So, I'm going to close today.